Hi, good evening. This video is a continuation of the last video or the first video, and this is a sample problem of the transform section method. We have given here, and the required are the moment capacity of the section. This is the section, cross-sectional area of the beam, and what uniform load can the beam carry in addition to its own weight. To solve the problem, we have what we call the procedure. Number one procedure, draw the transform section and the stress diagram. This is the transform section. And this is the stress diagram. Number two of the procedure is location of neutral axis. Neutral axis here is this one, this line, neutral axis. Before we go into solve the value of x, we compute first the modular ratio. This one, ES over EC, this one, and the result is 9.286. Say 9, which is greater than the minimum value of n, which is 6. Then the AS, the cross-sectional area of the tension bar. According to the NSCP specification, number 35 bar has an area of 1000 square millimeter. Since the tension bar is 4, so multiplied by 4,000 square millimeter. To transform the area, multiplied by n, which is 9, resulting to 36,000 square millimeter. For the compression bar, specification again, number 10 bar has an equivalent area of 100 square millimeter. Since this is 2, multiplied by 2 is 200. To transform the area, multiplied by 2n minus 1, resulting to 4,300 square millimeter. Then we have to solve the value of x. This is the equation. So, to solve the x, moment of compression area is equal to the moment of tension area. This one. This is the tension area, compression area, and this is the tension area. So 150, this one, 150 times the height, which is x, this one, 150 times x, then times the distance of the center of the gravity, which is x over 2 divided by 2. And since this area is identical with this, so multiplied by 2 to make it simple. Then again, plus the area of this area, this rectangular, 150, the base, 150 150 times the height. The height of this is this one. X minus 150. X minus 150 and times the distance of the center of gravity, X minus 150 divided by 2. Yan. Then plus the transform area of the compression bar. 3400 times X, this one, times X minus 60. And these are equal to this 36,000 times the 680 minus X, this one. Now, computing this value of X, it will be 284.340 millimeter. This is the location of the neutral axis. Okay. Number 3 of the procedure is the computation of the moment of inertia. Moment of inertia. Since our area is a rectangular shape, this one, the moment of inertia of the here to the in the neutral axis or X axis is 1/3 BH3. That's why done. And the moment of inertia at the center of the gravity is 1/12 BH to the third. So computing that, we will going to compute. Moment of inertia 1/3. Unahin natin. 1/3 times 300. I combine the 150 because this is identical. So 300 times the value of the height, which is X, 284.34 to the third. Then plus this one. This is rectangular. 1/3, 150 here. 150 times the 284.34 minus 150. This height is X minus 150. So that's why we have here plus the area of the transform moment of inertia of the transform section of the compression bar, which is 3400 times 284 minus 34 minus 3400 times 284.34 minus 60 to the third. So that is for the one. And then for the tension, 36 times 36,000 times 680 minus 284.34. And computing this, the moment of inertia is this one. Okay. Try to compute that. Try to compute the moment of inertia and the location of the neutral axis. Anyway, I will go into make a separate video for that competition, inshallah. Okay, we have now the value of x, the location of the neutral axis, and the moment of inertia. Now we will go into compute the flexural stress. For the concrete, FC equals x, which is less than or equal to 45% of the specified compressive strength of the concrete. So computing this one, it will give 9.45 megapascal, this one. So the moment capacity FC, this is the compressive strength of the concrete, times the moment of inertia over the x, location of the neutral axis. Substituting all the values, this is moment of inertia, and the x times 10 to the negative 6 to convert the units into kilonewton. So computing this, we have 273.420 kilonewton meter. This is now the capacity. This is now the capacity of the concrete section, for the concrete only. Next video, we will compute the flexural stresses of the steel bar in order to compare the capacity of the steel bar to the moment capacity of the concrete section. Whichever the less, that is the capacity of the section. So I will in the lecture this time, and inshallah we will continue.